Good evening everyone, I am S.M.K. E2256. Today I am presenting my progress on the performance and safety evaluation of R32 and blended refrigerant in split air conditioning systems. This research focuses on finding a safe, efficient alternative to high global warming potential refrigerant while solving the specific technical challenges of the R32 transition. My primary aim is to experimentally optimize the performance and safety of a R32 refrigerant in a controlled lab environment. Key goals include identifying the optimal mass for R32 systems to maximize efficiency and investigating the use of carbon dioxide as a thermal stabilizer and fire suppressant. We specifically target a 5 to 8 Celsius reduction in compressor discharge temperature to extend system life and aim for a final GWP of less than 450. As shown in my timeline, the project is divided into 5 phases. I have completed the title finalization and proposal presentation. I am currently in the literary review and execution planning phase. From week 10 onwards, I will move into full experimental execution, data collection and final calculations. My literary review has identified several critical benchmarks that guide this research. In terms of performance and efficiency, studies indicate that 0.3 to 0.7 ratio of R32 to R290 is often the sweet spot for balancing operational safety with high performance. Specifically, retrofitting an R32 unit with a 50% mass of R290 has been shown to reduce power consumption by a significant 40.2%. A key finding is the optimal charge rule. Research confirms that the highest coefficient of performance is typically achieved at a 95 to 100% charge mass. Exceeding this limit actually causes efficiency to drop. Furthermore, binary blends such as 70 to 30 ratio to R32 to R290 mixture have observed a 29.7% increase in COP compared to pure R32. Finally, looking at potential enhancements, adding R32 to pure CO2 cycles can improve system efficiency by up to 10.6 through better thermal matching. These findings validate my approach to using ternary blend to achieve superior efficiency while maintaining a safe operating environment. Under thermal and operational findings, POR32 is confirmed to exhibit high discharge temperatures peaking between 110 to 119.4 Celsius. High discharge temperatures leading to acid formation and potential compressor failure. Using R32 to R290 mixture allows for refrigerant charge reduction of 30 to 35% compared to standard R410A systems. The critical temperature of 68 to 32 ratio of R32 to R290 blend is 24.5% lower than pure R32, which significantly reduces the thermal load on the compressor. My project will experimentally verify if adding CO2 to this mix can further enhance these thermal benefits. Under safety and leakage dynamics, experimental data confirms that R32 leaks from a running unit in two distinct phases, fast leak stage and slow leak stage. In stagnant conditions, R290 tends to accumulate near the floor because it is denser than air, creating localized dead zones. In a typical ventilated room, the maximum concentration of leaked R32 generally reaches only about 15% of its lower flammability limit. This slide illustrates the benchmarks I aim to achieve during my experimental stage. By comparing the baseline of pure R32 with existing R32 to R290 blends, I have defined the specific targets for my proposed ternary mixture of R32 to R290 and carbon dioxide. These values are my success criteria. Once I enter the experimental phase, I will compare my real-world data against these targets. This result will directly decide my future steps, whether to finalize the current mixing ratio or to adjust the carbon dioxide concentration to further optimize safety and performance. I would now like to discuss the specific research gaps I identified during my literature review which justify the necessity of this project. The first major gap is the simulation between simulation and experimental disconnect. While there is a vast amount of literature on the theoretical modeling and simulation of low global warming potential refrigerant, there is a critical lack of experimental validation for these models in real world small volume environments. Most existing papers focus on ideal thermodynamic cycles, often ignoring practical factors like pressure drops and the complex interaction between compressors and lubricant and high temperatures. My project aims to bridge this gap by transitioning from simulation-based work to experiment-driven research by doing a physical test in a control cold room. Another gap I understand is absence of ternary blend data. Research is heavily concentrated on binary blends to replace R10A. The gap there is no documented experimental data on the performance of a ternary blend for residential split AC systems, example R32 to R290 and CO2, which means carbon dioxide. The gap we don't yet know how these three gases interact in terms of fractionation or if carbon dioxide can effectively suppress the high flammability of R290 without sacrificing the cooling capacity of R32. These are the references I follow. And that concludes my progress presentation. Thank you for your time and attention.